Okay, we will continue with our previous discussion where we had stopped with the definition of a interior point of a set, right, and the way it was defined was a point x in a set A is said to be an interior point, right, if you can find a neighborhood such that all its points belong to the set A, right. So, if there exists an open ball, right, we did not define what is a neighborhood, but we defined an open ball such that all its points belong to A. And then once you had the notion of interior point, then the collection of a set is said to be open if it contains all its interior points. So, now we know the definition of open set. So, let us see some properties of open sets. Right. So, this was interior point. So, the first property is arbitrary union of open sets is open. So, that means if you have a collection of open sets where AI is open, right, and then you take arbitrary union of open sets. So, if I call this as some A, then so each AI is open, then arbitrary union of open sets is also open. We will not prove this, we will, it is a property, right. One can prove that, but what is important is that you can show that arbitrary intersection of open sets is not open, it is not necessarily open. Example, you take intersection over the intervals of the form, open intervals of the form 1 by n, minus 1 by n, 1 by n, where n is a integer, right. So, this is nothing but the singleton, right, and we know that this is, we will later on show that this is not an open set. Next, we will move to the notion of closed sets, right. So, just like we define the notion of open set using an interior point, right, we will define a notion called an adherent point. So, let A be subset of Rn, and we want to define the notion of adherent point of set A. Right. So, let us see that. So, one way of defining closed set, we saw that the complement of open set is closed set, but we want to do it from basic definition, right. Yeah. So, given a set A, x belong to Rn, note that x need not belong to A, x is any point in Rn, is called an adherent point or a closure point of A if every ball around x contains at least one point of A, right. So, that means given a point x, you should be able to come up with an R, right. So, a ball centered at x and radius R such that its intersection with A is non-empty, right. So, here the key points are that The one is the x need not belong to the set A, x is a point in Rn, and you have to show that for every ball right around x contains at least one point from A, unlike the notion of interior point where we had to just come up with one ball, right. So, here you have to show every ball around x contains at least one point of A, right. Then x is said to adhere to the set A. So, in this figure, right, you can see that there is a set A, and I denote by dotted lines to signify that the points on the boundary do not belong to the set A, right. So, now obviously, if you take a point inside the set, then every neighborhood of this point, right, contains an element of the set A. However, if you take a point here, right, then no matter how small the ball you choose, you will never be able to if you take a point on the boundary, right, then you take any ball around this point, it will contain at least one point of the set A, right. So, in that way the point on this sitting on the boundary is also an adherent point. Note that that point does not belong to the set A, because as I said, the set A does not contain the boundary, right. So, it contains all points inside this dotted line. Now, so once we know the notion of an adherent point, right, then we can define the notion of closed set, right. So, set A, right, the set A is said to be closed if and only if it contains all its adherent points. Right. So, just like we define the open set using interior points, we can define the notion of closed set using adherent points. Again, properties of closed set, right. One is arbitrary union of closed sets is not necessarily closed, it need not be closed, whereas arbitrary intersection of closed sets is closed, right. So, for this you need to come up with a counter example, whereas here you will have to give a formal proof, right. So, we will not dwell into that. So, now once we have defined the notion of open set and closed set, we require what is known as bounded set. So, a set A is called bounded if it is contained in some ball with some radius and with some center x, right. So, here in this case I have two examples, right. So, this is a case of this is a set A, and you can bound it with an open ball with some center and some radius r, whereas this set, right, you can see that it is unbounded because this part it continues infinitely, right, it opens up infinitely. So, you will never be able to find a center x and a radius r such that this set is contained in a ball. Right. So, once you have the notion of a closed set and a bounded the notion of boundedness, one can define what is known as a compact set. But before we go that, we need another notion called the notion of limit point of a set. So, again A is a subset of Rn. So, we want to define the notion of limit point of a set. It is another way of characterizing a closed set. So, we will see that, we will see the definition. A point x in Rn is said to be a limit point of a set A if every neighborhood of x, right, contains a point of A distinct from x. Right. So, unlike an adherent point where every neighborhood of x contains a point belong to A, and that point could be x itself in the definition of adherent. Whereas, in the definition of limit set, the difference is that the every neighborhood of x should contain a point distinct from x. Other than x, you should be able to find a point from the set A. Right. Then that set, that point qualifies to be a limit point. Right. So, here I have an example to capture all the whatever notions we have studied. So, let us so here the in this case the set is union of three sets here, minus infinity to should have been minus infinity, there is a typo here, minus infinity to minus 1 union 1 to 2 union the singleton. So, we denote the singleton by this curly bracket, right. So, if you want to find the adherent points of this, the adherent points are obviously here all points from minus infinity to minus 1, again there is a typo here, it should be minus infinity, all points between 1 and 2, and also the point 3 itself, right. However, for the limits points, it is the whole of this interval, okay. But it does not include the boundary point, because if you take the boundary point, if you take the singleton 3, right, then you take any neighborhood around that point, right, then you will not be able to find a point of that set other than the point itself. So, the definition fails, and the boundary the isolated point 3 does not qualify to be a limit set, right. So, here is an example which illustrates the difference between the notion of adherent points and limit points. Again, one can characterize the closed set as a set A is said to be closed if it contains all its limit points. So, what is the relation between the set of adherent points and limit points? Sometimes it is also called accumulation points. So, the relation is that A closure, this is the closed set, is nothing but A union the set of limit points. So, this is the closure of A, and this is the set of limit points of A, right, or this is nothing but set of all adherent points So, basically in A prime, that is set of limit points, an element x is said to be belong to the set of limit points if x adheres to A minus the point x itself, right. So, we have the notion of now the adherent points, limit points, interior points, right, and also we have also seen the complement of the set, right. So, we will move further and define the notion of compact set. A set A is said to be compact if it is closed and bounded. Note that this is not this definition works in Euclidean space and not in some other topological space, right. So, there is a more formal definition of compact set, but since we are going to work in Euclidean space, this definition will work, right. So, set is said to be compact if it is closed and bounded. So, you can see here I have some examples, right. So, in R2 you have the closed balls, right, it is closed, right, that means the set includes all its boundary points, and it is bounded because you can always find a open ball with some center and some radius such that this set is contained in that. And here I have a example which is closed, but the set is unbounded in the upper half, right. So, I can never find an open ball which contains this set here. So, the notion of compact set is very important we will use that when we do the stability analysis, right. So, in fact, we will use that to characterize the notion of region of attraction of a equilibrium point. Next, we will move on to the notion of boundary of a set. Even though we have been talking about boundary of a set, we have not formally defined it, right. So, again A is a set subset of Rn and we want to define the boundary of a set. So, the boundary of a set is nothing but denoted by this symbol, is nothing but take the closure, right, intersect with its closure of its complement. So, the complement is A, right, and then take the closure. So, this is how the boundary of a set is defined, right, and it is quite straightforward to see that it is a closed set because it is a intersection of closed sets, it is a closed set. So, by boundary we mean pictorially we understand the boundary, but it is important that we need to go beyond pictures and apply the definition, and pictures are only the starting point to understand the definition, but one should move beyond the visualization. So, at this stage I think now we are in a position to take up an example and identify the interior points, adherent points, limit points, boundary points and the complement, right. So, I have the example here. So, let S is be a subset of R, okay. So, S is given by this interval. So, we need to find S interior. So, let me denote the interior points by this symbol, then S, that is the closure points, then S prime the limit points, and the boundary points. And we also need the complement. Complement of S, right. So, let me write down the set once again. So, it consists of union of 3 sets. So, note that this is a singleton set. So, S interior, right, should contain all points from minus infinity to open set minus 1, right, because if you take any point about minus 1, if say minus 1 qualifies to be an interior point, then any ball around that, right, will contain all its, I mean the minus 1 does not qualify to be an interior point, right. Now, what about this? So, 1 and 2 you exclude them, right, and we also know that the singleton is a closed set. So, we exclude the, and it is a closed singleton is a closed set. So, obviously, it does not qualify to be a interior point, right. So, the interior of set S is from minus infinity to minus 1 union 1 to 2. So, here as I said the minus 1 does not qualify to be an interior set, because if you take any neighborhood, right, however small, not all its points belong to the set S, right, because no matter how small ball you choose around minus 1, you will always get some points to the right of minus 1, which are not in the set S, right. So, the minus, so these points do not qualify to be an interior point. So, you remove them, and the way you remove is you put an, you make it as an open set, right. So, we denote open intervals by the round brackets. What about the S closure? So, the set of closure points of S. So, certainly it will include all points from minus infinity to minus infinity to minus 1 union. It will include the points 1 and 2, because about 1 every neighborhood will at least should contain at least a 1 point from the set, right, and obviously the number 1 is there in that set. So, it will contain all points between 1 and 2, including 1 and 2, and it also includes the singleton, because you take any neighborhood around the singleton 3, it obviously contains the number 3. Whereas S, the set of limit points, the only change is that it will not include the singleton. What about the boundary points? So, the boundary points are minus 1, right. Minus infinity is not a boundary point, it does not belong to the set, right. So, it is not a boundary point here. So, it will be minus 1, then 1, then 2 and 3. Okay. And finally, S complement is all points from R you remove the set S, right. So, you have from minus infinity to minus 1. So, minus 1 is included. So, I need to exclude minus 1. So, it is from minus 1, 1 is included. So, I need to exclude 1 union 1 to 2 is in set. So, I need to exclude 2. So, 2 to 3, because 3 is there. So, I need to exclude 3 union 3 to infinity. Sorry, this should be, yeah, this is okay. So, this is the complement of the set S, right. So, here is a example which captures the notion of interior points of a set, the closure of a set, the limit points of a set, the boundary of a set, and the complement of set, right. So, in Rn we have seen that closed and bounded sets are compact, right. In fact, on the real line the closed intervals are compact. So, on the real line closed intervals are also compact. Okay. So, that is an interval of the form are compact. Now, a natural question is, there are two questions that arise. Are there sets which are neither open nor closed? That is the first question. Then the second question is, are there sets which are both open and closed? Well, the answer is, we will answer the second question, right. So, are there sets which are both open and closed? The answer is yes. And what are those sets? In fact, the only sets which are both open and closed are the whole space and the empty sets. So, the only sets which are both open and closed is the set Rn and the empty set. Okay, we denote the empty set by this symbol. So, the question 2 was are there sets which are neither open nor closed? Well, on the real line, right. So, you can have sets which are like this, say this is -1 and 1. So, this includes all points excluding -1 right up to the point 1. So, this is an example of a set which is neither open nor closed. So, you can either call it as half open, half closed, or half. So, this is an example wherein in the real line. And what about the in R2? Okay, so this is in R, say in R2. Okay, so maybe you can have something set something like this, right. So, it includes all points inside this, but it does not include this boundary points, right. So, this is an example of a set in R2 which is neither open nor closed. So, we have seen now the notion of open set, closed set, compact set, bounded set, right. There is another notion called the notion of dense set. So, this is motivated by well known result in analysis which says that the rationals are dense in real numbers. That means, you give me any real number and you give me an arbitrarily or you give me any neighborhood or however arbitrarily small, you can always find a rational number sitting inside that ball, right, or in this case the interval, the open interval. So, let us see the definition. So, a set is A is called dense in Rn if A closure is the whole of Rn. Right. So, as I said, the well known example is the set of rationals. Having defined the notion of dense set, we are left now with one more notion, that is the notion of a connected set. So, let us understand what we mean by disconnected sets. So, it will be easy to understand what is meant by connected set, right. So, the picture below here is an example of a disconnected sets, that means they are not in one piece, right. So, intuitively it means that a set is said to be connected if it is in one piece, or it is said to be disconnected if it is not in one piece, right. But this is a very intuitive idea, and let us see what does it what is the mathematical definition of the connected set, right. So, there is a notion called separated sets or disconnected sets. So, two sets y and z are said to be disconnected if their union is the whole of the set x, and y closure intersection z and y intersection z closure both are empty sets. Right. So, that means they do not have the limit points the set Y does not have the limit points of Z, and so also the case with the set Z. So, once you have the notion of disconnected set, we say the set X is connected if you cannot find a separation. Right. So, let us make this little more formal. So, we are now talking about connected sets. So, I have an example. So, let me take A as 0 1, these are sets in R, and B as 1 2, right. Now, what can you say about A intersection B? It is a null set, because this 1 does not belong to the set B, whereas 1 belongs to A, right. So, their intersection is the empty set. Now, let us take one more example. This is example 1, we will call it as example 1. So, A is 0 1 and B is 2 and 3. Well, here too A intersection B is the empty set. And let me take another example where A is 0 1 and B is 1 and 2. Certainly, here A intersection B is not empty, right. So, if you apply the definition of two sets being not disconnected, so this example 3 fails. So, in that sense that they have a non-empty intersection. So, they cannot be separated, right. So, they are connected. Now, come back to example 1 and 2. What is the difference? Well, the difference is both have empty intersection. However, if you compute A closure intersection B, right. So, A closure is nothing but here A itself. So, it is A intersection B, and A intersection B is null set, and A intersection B closure is 0 1 intersection 1 2, which is non-empty, right. So, in that sense this A and B, right, are not. So, let us go back to the definition. So, are A and B disconnected? Well, for them to be disconnected, right, their intersections with the closures, right, should be empty, and that is not true in this case, because you have a non-empty intersection with one of the two cases, right. So, A and B are not disconnected. So, that means they are connected. So, here is an example. So, this example, it is a connected set, right. What is the connected set? A union B is a connected set, it is in one piece. Okay. Whereas, here if you do A closure intersection B, right. So, it is 0 1 intersection 2 3, which is empty, and so also A intersection B closure, which is 0 1 intersection 2 3, which is empty, right. So, it satisfies the definition of two sets being separated, right. So, they are disconnected. So, this is an example which is not connected or disconnected, or we also use the word separated, right. Whereas, here obviously they are not separated. So, they are connected. Here things are little obvious because both have a common point 1, but in the example 1 things were not very obvious because one is not common to both, because in one of them one is a boundary point, whereas in the other it is an interior point, right. But by our notion of connected means that one of the sets should contain the closure of the other set, and so also in the other way, right. So, we have now more or less dealt with all the notions of sets, right. We have few more notions remaining, and we will continue it further.